So hi everyone, my name is Aldana Grichener. I'm a postdoc at the University of Arizona. And today I'm going to talk to you about how we can use machine learning in order to make better progenitors for core collapse supernova simulations so we can get more insight into the formation of neutron stars and black holes. So as Adam Burrows showed us at his beautiful talk on Monday, in order to study supernova explosions, we need to perform 3D hydrodynamical simulations where what we do is we basically explore the star and the shock that propagates throughout the star after the core collapses. But in order to be able to actually perform the simulations, we need to have these models of massive stars that are the supernova progenitors that you can see over here as a starting point. So basically what we do is we use 1D stellar evolution codes like MESA or Kepler. We evolve the massive star that would blow up as a supernova up until the phase when the iron core starts collapsing inwards. And when it collapses inwards fast enough, we freeze the simulation and we move this progenitor with the structure that we see here to the 3D simulations and basically explore the propagation of the shock from there using the 3D hydro. But it turns out that actually the task of making these progenitors for the core collapse supernova simulations is a pretty hard task. And actually we know that while stars spend most of their life burning hydrogen into helium in the core, about 95% of the time of the simulation actually goes to late burning stages, to the stage what we call silicon core burning, when we are forming the iron core that would end up collapsing. And the reason for that is because of the bottleneck that is posed by nucleosynthesis. So to simplify this, what happens is that in order to perform silicon core burning, we need hundreds of isotopes, at least 100. 100 isotopes mean a differential equation set of 100 fully coupled differential equations, because they're coupled because the way that stellar evolution codes handle this nuclear burning is by having this nuclear reaction network, which is the list of all the isotopes that the code knows about, and the list of the reaction that correlates between their formation and destruction. So every time we add one more isotope, we add actually one more equation that is coupled, and when we couple all of these with the stellar equations in the stellar evolution code, then everything gets really stiff, and many times the code ends up crashing without being able to produce these core collapse supernova progenitors. So this is a real bottleneck for the formation of supernova progenitors for multidimensional simulations. And one way that we handle doing this is by using these small nuclear reaction networks that are nuclear networks of about 20 isotopes or so. So these networks, what happen is that they're fake reactions that are actually tweaked in order to reproduce some of the values that are relevant for supernova explosions, like the electron fraction or the central density. But you can see over here, if we look during silicon core burning, then giving the same initial conditions to a large network and a small network and evolving for the same time give us completely different nucleosynthesis yields. And these nucleosynthesis yields would affect the burning that occurs in these phases that can lead to completely different explodability outcomes. So actually using these small networks to study massive stars on the latest phases that lead to core collapse supernova is not good enough for our needs. So the way that we try to tackle this in a collaboration with Mathieu and Selma that are here in the program and some other collaborators is by using emulators, meaning a neural network framework that emulates the nucleosynthesis during late burning stages. So instead of having to actually solve these differential equations coupled to everything, what we need to do is have these neural network trained models that would predict what are these typical nucleosynthesis outcomes. And the way that we do it is that we will design this deep feed-forward neural network framework, which basically what it does some sophisticated feeds between the input and the output layer. We have as the input the temperature, density, and composition of a burning shell. We map it throughout the neural network and obtain what would be the typical output of the composition, energy generation in nuclear reactions, and energy that is lost by nuclear neutrinos. So we take these neural networks, we train them on a lot of data that is generated by the nuclear module of MESA, and then we use another subset that we didn't use during the training to try and predict how well these neural networks perform. So you can see over here the typical error in the abundances, which means, okay, so the error here would be how well the neural network predicts the results of the large 150 isotope networks. So it's not like we can never get something that is better than the large network. So in our case, like the large network is the absolute truth, which can be problematic because still we have lots of nuclear physics uncertainties. But for this case, what we're trying to get is basically something that is better than the things that are already implemented in stellar evolution codes. So for the abundances, we see that on an average case, we have still pretty large errors. But when we go for a typical stellar composition that has average error in other quantities, then we can see that the neural networks do actually a pretty good job in reproducing the main nucleosynthesis yields, while we still have some discrepancies in the abundances. But I'd be a bit more worried about these discrepancies if I didn't remember how these compare to the small networks that I showed you a couple of slides ago. So just to put everything one next to the other, here we have the large networks, which is what we want to obtain in the simulation. Here we have what the neural network predicts for the same initial conditions. And then we have what the small networks that are implemented in many stellar evolution codes give for the same initial condition, which is completely off in most of the isotopes. So when going a bit further and looking at the electron fraction, we see here we compare the error in the electron fraction of the neural network compared to the large network that is represented here in these green crosses for the different time steps that we trained in our simulations. And here in blue, you can see the error of the small network that is currently used compared to the large network. So we can see that we have a 3 to 4 times improvement that, okay, with uncertainties, you might think that is not such a large improvement, but actually because the electron captures is what ends up blowing up the star, and because the electron fraction goes in a quadratic term in the effect under mass, which is the maximum mass of the iron core that can still sustain itself due to the degeneracy pressure, then having this improvement in this change in electron fraction can really change the results of explodability. So the same goes for the nuclear energy that is generated in these nuclear reactions, where we see that we can have a 3 to 8 times improvement when looking at the errors of the small network compared to the errors of the neural network. So this is pretty seem to be going into the right direction, and this looks promising. So when thinking about implementing these in stellar evolution codes, we can see that when we do a simple test to try and understand how much more speed up we will have while using the neural networks compared to the large network, for a case of nucleosynthesis data of models that have fully converged, like we didn't have this problem of the time step going smaller and smaller and smaller up until the phase when the models crashed, you can see we have up to a 30 times speed up, while we're also getting a free speed up compared to the small networks, we're giving more accurate results. So this is actually not taking into the account all the models that are not going to end up converging during silicon core burning, which, let's face it, is the majority of models. So, and it also doesn't take into account all the human time that goes into numerical stabilizing it, trying different things, rerunning these, and so on. So the speed up would be much more significant than what the simple test gives. But in order to be able to actually use these in stellar evolution codes, then we still need to first train on a larger parameter space, train on things that are more oriented to stars, mixing more stellar compositions. And I think the most important thing would be to assess the compounding error, because all of this was done for one time step, but the stellar evolution code is going to take a series of time steps. We have some estimations of that I don't have time to go into, but we can talk about it afterwards if you are interested. And we also need to see how well the energy is conserved and impose some things on that, because we are emulating the energy directly and not taking it from the nucleosynthesis. So I think this could have really great implications on the formations of Supernovae and black holes, natal kicks, and everything that's related to binaries, just because we will have more progenitors to provide for the three-dimensional simulation, so we can study it more and get more trends. And continuing in the line of shameless advertising, so thank you, Tomer, for making this more easy for me. Then if you're interested in nuclear astrophysics in general, like how nuclear astrophysics is related to explosions, to stars, and now we go to galactic and chemical archaeology from there, using with emphasis of machine learning stuff and new surveys, then we're hosting a nuclear astrophysics workshop in Tucson in March. So I also put the link on Slack to the ones that are interested. So I'll leave my take-home messages here, and I hope I convinced you at least that small networks are not good enough to do the multidimensional simulations, and that we have some promise here, but we still need to work on it in order to actually implement this in stellar evolution codes. Thank you.
Maud Gold from, I guess, Caltech and Carnegie. Really interesting talk. I was kind of wondering if you've explored different neural network frameworks to do this. I'm thinking maybe like physically informed neural networks. Yeah, or can you comment on this?
Yeah, so I explored different frameworks in the sense that I played with lots of things like the number of layers, the number of neurons per layers, the different loss functions, and different connectivity between the networks. I didn't go into the direction of physically informed networks, though it's something that I've been talking about and trying to see if it makes sense for this problem. And something else that I would like to explore is also like time series neural networks that kind of connect between the different time steps.
Yeah, Adam Burrows. This is, of course, important for getting, for example, MESA models actually converge a good fraction of the time. That would be very important. First, on what time scale do you think you might have something like this embedded in a stellar evolution code that we could use?
So it's a tricky question, because in order to know that, what we need to do is implement what we already have and see how far off we are from from where we would like to be. Like, I think the major issue would probably be the compounding error. Right now, where we do the simple test of like running the neural network on its own output, then we're getting actually pretty good results in the sense that the errors in the electron fractions are still twice higher than what we show here, but twice as lower than the case of the small network. But still, this is not exactly what we will be doing in a stellar evolution code, because you will have mixing and remeshing of everything and things like that. Right now, I just won a computational grant to have lots of access to CPU hours from January to September. So I hope to push it forward using this computational grant.
Now, it's quasi-equilibrium that is the most difficult, the silicon burning phase. And people have studied putting together clusters of isotopes, and that has generally been, at least in the past, has been very productive and very interesting. Certainly, it does reflect the physics of the process. Have you thought about trying to look at those clusters? Because in your training, you're implicitly actually finding those clusters.
Yes, so that's actually something that we tried to do, like the training by clustering different groups of isotopes and effectively doing like a small network, but like in a way of quasi-equilibrium, and it didn't actually work quite well. But I think it also can have to do like with the fact that because of all of these kind of unexpected pathways that the nucleosynthesis can take, there are really large tweaks that the network had hard time actually mimicking. Okay, doing the quasi-equilibrium like itself without machine learning, I think that is something that was tried with MESA. I think Matthew can comment on that, but I don't think it was successful.
There was a PhD thesis by Ray Fix with Friedel Thielemann. I was wondering whether that could have been informative.
Other questions? Okay, go.
Sorry, Adam Burrows.
Nice to meet you.
So you have the full calculations of the full network. You have the neural network calculations, and you have the small network calculations. Do you carry those when things converge for all three of them all the way up to core collapse?
So right now, the things that I presented were done for one time step at a time, meaning we have different models trained for time step from 10 to the minus 6 second up to a time step of 10 to the 2 second. We are doing tests like with actually doing the series of time step, but it's not something that we carried like thus far.
Okay.
Like we are pretty much at the state of like a proof of concept, like showing that this is a method that could be useful, and then from there trying to actually tweak everything to actually put this in the stellar evolution code and see how well it works.
Okay, let's thank Aldana again.